Hello, and welcome back to Aerospace and Mechanical Lab 1. Today we are going to talk about wind tunnels and force calculations using a wind tunnel. Okay. We will talk about history of wind tunnels, where the wind tunnels come from, and how we can do analysis with them, different types of wind tunnels and different sections within a wind tunnel. Then we will move on to talk about force measurements inside the wind tunnel and other types of measurements we can make inside the wind tunnel. We will talk about force coefficients, and eventually we will talk a little bit about the lab itself. Okay. Wind tunnels are devices that are used to accurately simulate the fluid flow in an atmospheric vehicle. What do we mean by atmospheric vehicle? It essentially means that whatever that can move within an atmosphere. It doesn't have to be Earth atmosphere, it doesn't have to be an aircraft. So we can talk about cars, we can talk about bicycles, and we can use all of these vehicles and test them inside a wind tunnel. Wind tunnels in general can measure forces, moments, pressures, shear, temperatures, and they can be used for flow field visualization and measurements of velocity, vorticity, and pressure of a flow field. Wind tunnels have different sections. They have the test sections. This is where you put your specimen, your sample in to make measurements, to record data. And they are, in general, they have an inlet, which is usually a convergence nozzle, and they have an outlet, which is usually a divergence nozzle. This whole shape is called a venturi. And the reason subsonic wind tunnels specifically are designed this way is because when you reduce the cross section, you're going to get faster velocities. So we can have a higher speed operating wind tunnels with a smaller test section compared to the inlet and the outlet. And the motor that is responsible for sucking the air or pulling the air in can be placed after the test section or before the test section. The wind tunnel we have in our lab is actually a wind tunnel that has its motor in front of the test section, before the test section, upstream of the test section. So there are benefits, there are challenges with all of these configurations, which are out of the scope of this lecture. Okay, the earliest wind tunnel that was used for scientific modeling and analysis was developed by Eiffel. Mr. Eiffel, who is essentially the principal architect of the Eiffel Tower, engineer behind the Eiffel Tower as well. And this was placed at the feet of the Eiffel Tower. This is an open return wind tunnel. What does an open return wind tunnel mean? It means that open return wind tunnel pulls the air in from the atmosphere, the surrounding atmosphere, and put it out from the exhaust inside the same atmosphere. So your operating conditions are always limited by the atmosphere around you, like the pressures, the density of air. All of those are limited by the atmosphere around you. But this is one of the earliest recorded versions of the wind tunnel that was put in use for scientific analysis. As you can see, it has a test section in front of, before the fan or the motor. So the fan is essentially just sucking air in to the test section and makes the wind tunnel ready for the analysis. Another early example of a wind tunnel was used by the Wright brothers. The Wright brothers were working on designing a plane, as you all know, but they couldn't really fly their planes because they were using data that was given to them by the different source. So one day they decided to actually do all of the measurements themselves and base their designs on their own data, not on someone else's data. So they built this wind tunnel, this manual wind tunnel. You can see the fan, which is after the test section, and the fan is was connected to a bike, and someone would ride the bike, and this will turn the fan, and the fan would suck air in the wind tunnel. And this is how their sample set up would look like. They usually have a sample installed. This is an airfoil, which is essentially two-dimensional cross-section of the wing. And they put it inside the wind tunnel. They do the analysis with it. They could change the angle of attack for the wind tunnel, which is essentially the direction between this structure of the wing, the angle between the wing itself and the direction of the wind. So the angle between the direction of the wind and the wing or the airfoil itself is called the angle of attack, which is the angle at which wind attacks your object. So they had this was a very simple wind tunnel, but they could make a lot of different measurements with it. So it was very useful. And based on this, they developed their own data, and they were able to fly their aircraft in North Carolina. Since then, wind tunnels have become more and more popular throughout the years. As you can see, in the 1980s, for example, we did a total of 10 years of wind tunnel testing for a space shuttle, for example. This is a huge number of tests compared to the number of tests the Wright brothers did. So you can see wind tunnels have become more and more popular, which does make a lot of sense because they are very useful in designing atmospheric vehicles. Modern wind tunnels look more like this. Like if you go to NASA or Boeing or any of these big aeronautical companies, specifically, they have rooms that are wind tunnels, essentially. You have the inlet in front here and the outlet in the back of the wind tunnel, and they design these true size, real size scales of their aircraft or cars and put them inside these wind tunnels to do aerodynamic analysis and measure the aerodynamic forces. Can have different types of wind tunnels. The ones you have seen so far are always open return, meaning that we have a motor that is responsible for sucking the air inside the wind tunnel or exhausting the air from the outlet. But another popular form of wind tunnel is called a closed return wind tunnel. The closed return wind tunnel essentially means that it is circulating the gas inside. The reason for a closed return wind tunnel is interest in doing simulation or analysis for special atmospheric conditions. For example, if you want to do a wind tunnel test on a device that is supposed to move on Mars, you can't really run a wind tunnel test in an open return wind tunnel. You have to use a closed return wind tunnel that is sealed from outside, so you can simulate the Mars's atmospheric conditions. But the problem is we cannot really have a closed return wind tunnel that is the size of these examples. Okay, so what should we do? We will talk about what we should do to design a smaller wind tunnels and scaled samples and use those numbers for the bigger actual vehicles. We will talk about this later on. But before talking about the scaling issue, let's talk about the aerodynamic forces first. The aerodynamic forces of interest to us is called, one of them is called lift, which is the force that is pushing your aircraft or your car upwards, and drag, which is pulling your aircraft back. So if you're sitting in an aircraft, generating lift is always beneficial because you want to be able to have a force that counteracts your weight. So you can fly, you can float in air or atmosphere, right? But having drag is not useful in most scenarios because it is essentially pulling your aircraft back where you want to go forward. So our goal in aerodynamic analysis, at least in aircraft aerodynamic analysis, is to maximize lift while minimizing drag, which essentially means that we want to maximize lift to drag or over drag ratio. And in this lab, we will only care about these two forces, lift and drag. Okay, so we know the aerodynamic forces, we know how we can use the wind tunnel. Let's talk about how we can actually make the wind tunnels smaller. Essentially, instead of using these huge wind tunnels for our analysis, we want to know how we can actually use a smaller wind tunnel like ours to do real testing on moving atmospheric vehicles. We have to use a concept called flow similarity. So using flow similarity, we can run the test on a smaller sample. As you can see, the one in these pictures here is a smaller sample of a F18. The idea is we can use this sample, we can do the analysis, make the measurements for this sample, and use the data for this smaller scaled aircraft to analyze the movement and the forces on the big real world true size F-18 aircraft. How we can do this? Again, we need to use the flow similarity concepts. What does the flow similarity concept tell us? It says that if you replace your forces with dimensionless forces, you have effectively made your forces independent of the size of your sample. So essentially, if we come up with a new variable that can replace force for us, we can use those measurements for a smaller scale model for the bigger true size version of our scaled model. That's the idea. So the goal is to come up with dimensionless parameters. And we have seen dimensionless parameters in fluids, like you can think of Reynolds numbers. It's the most famous dimensionless parameter. So we have to replace our force with a dimensionless parameter that can be used independent for a specific flow condition, for a specific geometry, independent of the size of your vehicle. And the two dimensionless parameters we're going to use are called the lift coefficient and the drag coefficient. So C of L, coefficient of lift, coefficient of drag, C of D, coefficient of drag. How do we calculate these? You have to measure the lift and divide the lift by the dynamic pressure, which is 1/2 density or rho multiplied by velocity squared, multiplied by the surface area of your vehicle. Okay. So we have to be able to measure the lift. We have to be able to calculate the surface area. We have to know the density of atmospheric conditions, atmospheric density essentially, surrounding atmosphere specifically, and we have to measure the velocity. Area calculations, simple. You have to get a caliper, ruler, or tape measure, whatever, to calculate the area of your sample. Lift is something that is measured by the wind tunnel. Density, we can Google at the specific atmospheric conditions what the density is. The only thing that we don't really have any information on is the velocity. Which essentially means that we have to have a sensor that can measure the velocity for us. And we do have a sensor for this. That sensor is called a pitot tube. A pitot tube is a sensor that measures total pressure and static pressure, and using this information calculates the velocity for us. So in the lab, the flow meter we have is connected to the pitot tube and does this calculation for us automatically. So you actually are only going to read a velocity, nothing else. You don't really need to calculate the pressures and then calculate the velocity. You can just read the velocity off the sensor. So when you have the velocity calculator, you can calculate the surface area, you have the lift. For your sample, you can calculate the lift coefficient, and the idea is that lift coefficient should be the exact same lift coefficient for a different size vehicle. It has to be the same vehicle, same geometry, at the same flight conditions. So the idea is, again, flow similarity. As long as you keep the flight conditions and the geometry the same, size does not matter, and lift coefficient and drag coefficient remain the same. Okay, so What do we need to do in this lab is to measure lift, velocity, and drag and velocity, and also the surface area, calculate the surface area at different flow conditions to calculate the lift and drag coefficients. That will be the first part of the experiment. You're given two different spheres, it's the same material, same everything, and then you have to calculate the drag coefficient for them. You have to compare the value of drag coefficient. The idea is drag coefficient for these two spheres must be the same, because the only thing that is different between the two is going to be their size. Everything else is the same. You will be also given a different material sphere, and you will see how the material can have any sort of effects. You essentially have to investigate is whether the material has any sort of effect on the drag coefficient specifically. Next part of the experiment is to use a teardrop shape that resembles an airfoil like this. An airfoil like this. And then calculate the lift coefficient and drag coefficient at a specific velocity. Change the angle of attack. That is done automatically. Just have to press a button and run the test again. Calculate lift and drag coefficient and give us a graph for lift coefficient versus angle of attack, like this graph. Drag coefficient versus angle of attack, and lift coefficient versus drag coefficient at different angles of attack. Your lift to angle of attack graph must look similar to this. It must have a linear region. It has to cross zero, usually at zero angles of attack, and it has to have a maximum, a local maximum. This local maximum, and I mean our focus is going to be on this region specifically, the linear region where the flow is attached. So we go from zero lift coefficient, which essentially means that zero lift, to a maximum lift coefficient, which is called the stall condition. The stall is, if you want to think of this in terms of solids, it is analogous to the yield point, where the material yields to plastic deformation. This is where the flow is completely separated and the vortex shedding happens. Then you will see a dip in lift coefficient. There is another point of interest, this point where the lift is zero. We want to know at what angle of attack, again, a usually negative value, your lift is going to be zero. So you have to graph this line for us. You have to identify the stall point and the zero lift angle of attack point. And this has to be done for the teardrop shape, again at 3 different velocities. Thank you for listening. Please let me know if you have a question, and enjoy the rest of your day.